Hello viewers, welcome to video number 75 of the channel Chemphilic, and video number 75 is the 17th episode of Chemical Thermodynamics. The topic of this 17th episode of Chemical Thermodynamics is work done in isothermal reversible expansion of ideal gas. So let's start. Reversible expansion already I have explained in my earlier video. Just imagine a gas is enclosed in a cylinder and it is attached with a weightless frictionless piston, and just imagine above the piston you have kept one funnel where you have taken some sand particles. Okay. Now, when the piston is in the stationary state, this piston is movable, stationary state, then this pressure of the gas is equal to this external pressure, that is P external. Now just imagine you have removed just one sand particle, that means very less weight. So therefore external pressure will be decreased by a very small amount. So when the external pressure is decreased by very small amount, then the pressure of the gas is slightly greater than external pressure, and this piston will move through a little distance, very small distance, say dl. That means overall there will be a small volume change. Like that, once again if you remove another sand particles, then what will happen? Again you are decreasing the external pressure by a infinitesimally small amount. So when you are decreasing the external pressure, again the pressure of the gas is slightly more than that of the external pressure. Again the piston will move. So if you repeat this process again and again, finally a finite volume change will happen. That means initially volume was V1, finally volume will be V2, that will be the expansion, and this process is the reversible process. So this is reversible expansion of the gas. Now we are considering, or we are going to calculate the work done in isothermal reversible expansion of ideal gas. So just imagine we have taken one ideal gas enclosed in a cylinder and it is attached with a weightless frictionless piston. That is the ideal condition, but practically that is not possible. Weightless frictionless piston. Okay, and this system, what is my system? This gas, this ideal gas, it is in thermal equilibrium with the surrounding. Now if you decrease the external pressure by infinitesimally small amount, then the gas pressure will be slightly greater than that of the external pressure, and the piston will move a little distance. That means who has moved the piston? Gas. That means work is done by the gas, and it is expansion. During expansion, work is done by the gas. So let's write. So let us consider an ideal gas is enclosed in a cylinder which is attached to a weightless frictionless piston. Though practically it is not possible. The piston is movable. And one more thing we consider, the system means my ideal gas. System is in thermal equilibrium with the surrounding. That means temperature will remain constant throughout the process. Okay, so it is isothermal process. Okay. So this is the condition. Now, initial volume of the gas is equal to V1. At the static condition of the piston, that means piston is in stationary state, piston, P external is equal to P gas. So it is in the static condition, that means downwards pressure is equal to upwards pressure. Now let external pressure is decreased by an infinitesimally, that means very small, infinitesimally small amount, say dP. Okay, then pressure of the gas or the gas pressure will be slightly greater than external pressure, that is P external. Under this condition, the piston will move upward direction through a small distance through a very small distance, so it is dl. Okay, so therefore what happened? Therefore slight expansion of the gas takes place. If the process is repeated, by a large number of times, then finally finite expansion of the gas occurs. Finite expansion of the gas occurs. Okay. Now let's derive. Now see, initially external pressure I am denoting by P external, and then in the first small step, it is decreased by the amount dP. So after the first step, final pressure will be P external minus dP. This is the final pressure. Okay. And now the work done during expansion, work is done by the gas. So work done, W will be is equal to here in this first step, small expansion. So W will be is equal to P external minus dP, and then increase in volume is already I have written, very small increase in volume, that is dV. So work done expression in the first step, that will be P external minus dP. Little bit you have decreased the pressure and the gas work against this external pressure, that is this final external pressure, P external minus dP, and change in the volume is dV. Now, when the piston is in the stationary condition, that means initially pressure of the gas is equal to P external when it was in the stationary condition, right? So now I have reduced little bit of external pressure. So in this case of P external, you can also write the pressure of the gas, that is P. Okay, it was equal. And now I have reduced little bit by dP. So this part P external is equal to pressure of the gas. Therefore, while doing this derivation, here you can write it as P also. So W is equal to, I can write it as, what is that? P minus dP, then dV. This is for one step. Like that, a large number of steps to be performed, and then finally the volume will be increased from V1 to V2. Okay, when a large number of small steps will increase the volume from V1 to V2. So volume increases from V1 to V2 after a large number of small steps. Okay. So what we can write, this total work done, this is your del W in one step, small amount of work done. So total work done, here also this is small amount, so this is del, I have to write this type of del. So del W is equal to this one. So total work done, W will be is equal to what? W will be is equal to V1 to V2. I have to integrate this one. Then P minus dP into dV. Okay. Now, so here from here I can write W is equal to what I can write? Integration from V1 to V2, then P dV minus dP dV. So dP is a small quantity, dV also small quantity. Small quantity, if you multiply by another small quantity, that result will be very, very small. So we can neglect this dP dV. This part we can neglect it. Okay. So therefore, work done, this W will be is equal to your V1 to V2, then P dV. Okay. Now, so P dV is the work done in each small steps, whereby the volume increased from V1 to V2. So this pressure is constant for each small step, but for all the steps it is not constant. So this pressure I cannot take it outside of the integration sign, because for one step it is constant, for all the step it is not constant. First step it is P external minus dP, next step P external minus dP, like that. It is decreasing slowly. So now we know that PV is equal to nRT. So P is equal to, we can write it as nRT by V. So putting this one, so this we can write it. So now if I put this one here, so W is equal to V1 to V2, then nRT by V, then dV. Okay. Now in the next step, so here W is equal to nRT. N is number of moles constant, R is universal gas constant, temperature T is constant because isothermal process, system is in thermal equilibrium with the surrounding. So all these things we can take outside of the integration sign. So what is left over? V1 to V2, then dV by V. Okay, so your W will come out as W is equal to nRT, then V1 to V2, integration of 1 by V dV, that will be is equal to ln V. Then we have to write lower limit and upper limit. Okay, so W will be is equal to nRT ln upper limit by lower limit, that is, upper limit minus lower limit. So ln means V2 by V1. ln, if I want to convert it to log, then W will be is equal to nRT into 2.303 log, then V2 by V1. Okay, and here work is done by the gas. Okay, work is done by the gas means this sign will be negative. This also from the derivation also you can show it. I will show you. Sign will be negative. Achha. Now we know that at constant pressure, okay, at constant temperature, according to Boyle's law, what we can write at constant temperature? P1 V1 is equal to P2 V2. So V2 by V1 will be is equal to P1 by P2. So this one you can write it as this W, or if I consider work done by the system, that is minus W will be is equal to, here it is work done by the system, that's why the minus. Okay, I'll show you, this can be shown from the derivation also. So minus W is equal to, what we can write? 2.303 log, or I can write, or this one, into nRT, then log P1 by P2. So these are the expression of work done by the gas during isothermal reversible expansion of ideal gas. So these are the expression. Now here once again you see, as I told you, sign will automatically come. How the sign will automatically come? See, here we have written in one step that work done, W is equal to V1 to V2, then P dV. Okay. Now P is the external pressure. Actually external pressure here, as the amount is value is same for gas, so I have written here P. But extra gas is working against the constant external pressure in each step. So therefore this is minus, external pressure is decreasing, so minus, and volume is increasing, plus minus minus. So therefore I can write it as minus V1 to V2, okay, minus V1 to V2 P dV. Understood? Because external pressure is decreased. So if I consider the proper sign here, then you see automatically W will come negative. If I consider the proper sign, then it is minus, volume is increased, that is plus, plus minus minus. So it will be minus integration of V1 to V2 P dV. So what will be the result? In that case, W will be is equal to minus nRT, then ln minus nRT ln V2 by V1, or W is equal to, say minus sign, automatically it has come, minus nRT into 2.303 log of V2 by V1. Okay. So work done by the gas, you are considering negative sign. Now if you put the proper sign here, and then if you proper sign in the sense pressure is negative here, then if you do the derivation, then here itself, in the derivation itself, it will come as minus. So this is the work done in isothermal reversible expansion of ideal gas. Okay, hope you have understood. Thank you.